All right. Thank you all very much for having me today. So I'm really happy to be here to tell you more about the Biomedical Data Translator that you've heard little snippets about all day from different speakers. So I'm Tyler Beck. I'm a program director working for the Office of Drug Development Partnership Programs at NCATS, which is a branch of the NIH. So I want to start by talking a little bit about myself, saying that my training is not in computer science. Though I've gotten the chance to dabble over the years, and that's been great. My undergrad degree was in bioinformatics and computational biology, so I did get to do some programming during that time. But then I went on to get a PhD in molecular and human genetics at Baylor College of Medicine, where I really focused on lab-based work. And then I did a postdoc at the National Human Genome Research Institute in Les Biesecker's lab, where I worked mostly on next-generation genome-wide sequencing. And I was lucky enough to work on a project that really caused some waves in that field, and it really kind of pushed my career forward, and that's how I ended up at NCATS. So this is all to say that I really have understood part of what I've heard in every talk today, but definitely not all of it, and I won't hold it against any of you if you're in the same boat when I start talking about biology and medicine during this talk, so that's where we're at. So now let's talk about where I am, which is at NCATS. So NCATS is the National Center for Advancing Translational Sciences, one of the ICs, or Institutes and Centers, of the NIH. NCATS is a disease-agnostic institute, part of the NIH, which means that unlike other institutes which focus on a specific disease type or a body system, for example, the National Cancer Institute focuses, of course, on cancer research, NCATS doesn't have that kind of focus. So instead, we're focused on translational science as a whole, which is the science of getting treatments from bench to bedside. In other words, helping getting new treatments from the state of early research all the way to treating patients in the clinic. NCATS is a small center, one of the newest ICs at NIH, and so we have a small budget because of this. One very interesting thing about NCATS is that we don't have an R01 research program, unlike many of the other ICs. We instead focus on smaller research grants, which are designed to accomplish a very specific goal, and often on more innovative funding opportunities like challenge prize competitions and other transactions awards. Now, while we don't have a disease focus, we do focus generally on research on rare diseases, because in many cases, these diseases are understudied and underfunded. And as I like to say in all of our messaging, rare disease is not rare. With an estimated 30 million people in the United States affected by one of the 7,000 or more different rare diseases. Within NCATS, I work for the Office of Drug Development Partnership Programs, so we have an even more specific focus on speeding up the development of new drugs and on drug repurposing. So I'm a program director for two programs, the Biomedical Data Translator, which is what I'll be focusing on today, and also another exciting program called LitCoin. As part of these two programs, I have a very small portfolio of awards that I oversee when compared to other program officers at NIH. But the reason is that the awards that I oversee are very time intensive. In my role in Translator, I am the main scientific oversight for the program. I'm in charge of reviewing and approving budgets and milestones for all the research teams. I attend the majority of the weekly working group and committee meetings, and I lead the decision making on the higher level program priorities at all levels. So now let's talk about the reason that I was invited here today, which is the Biomedical Data Translator. So what problem are we trying to solve with this program? Really, the issue we've run into many times in the past is that clinicians and bench scientists think about disease in a fundamentally different way. Physicians diagnose and treat based on signs and symptoms affecting specific target organs, whereas researchers really think of disease more in terms of molecular changes in genes, proteins, pathways, or cell types. And so our goal is to try to translate the knowledge from one side of this chasm to the other. Because really, the data is not the problem, it's making connections between the different types of data that is the issue when it comes to trying to solve these kinds of problems. So, Translator is designed to help surface knowledge from a vast array of biomedical data, augmenting the reasoning of researchers to help them find new relationships between data points that are relevant to their research. This is done through the use of several separate knowledge graphs, all connected through a set of knowledge tools, essentially a large cloud of connected data like you can see on the screen. Translator uses information structured in this way to traverse the data and present to the user the relevant connections. Translators' knowledge graphs are generated from a huge list of public data sources, including those supported by the NIH directly, like PubMed, GARD, and PubChem, along with public databases like Chembol, Reactome, SNOMED, and many others. It's worth noting that getting all of these disparate data sources to interact with each other is, in a coherent and valuable way, is a huge task. And it's one that's been tried by other groups many times before with relatively little success. Having a single language to describe concepts across all of biomedical science is a huge undertaking, and we've created several new standards as part of our work over the last few years, some of which are starting to be used in other large data science projects. All right, so Translator is a system of software tools currently built by 14 teams, all funded through the Other Transactions Authority, plus a user interface team under contract to us for the development of the user interface, and a group of intramural scientists working directly for NCATS. We have several different types of teams as part of the consortium. So first up, we have the knowledge provider teams. And so knowledge providers are tasked with searching for and collecting data from databases around the web. The databases that these knowledge provider teams ingest can often answer the lowest complexity questions that our users might pose to the system all on their own, like looking up what cell type a given gene is highly expressed in, for example. These teams take the underlying data from many public data sources that fit within a specific knowledge domain and build knowledge graphs within that domain and serve as the expert source for that type of knowledge. So for example, we have a genomics data provider, a clinical data provider, and a chemical data provider, and several others. Then we have the autonomous relay agents, or ARAs. They're sophisticated reasoning tools which access the graphs that the knowledge providers serve up, requesting specific parts of those underlying knowledge graphs based on what the user has asked the system. They then combine those different results into a new graph, which includes knowledge from many different domains all connected together. Next, the ARA will find a path through the knowledge graph that may satisfy the criteria of the question that the user asked, and therefore could be an answer to the query. These results are also ranked based on things like confidence scores and other metrics, and each ARA has their own way of doing this ranking of their own answers. Finally, each of these potential answers from all the different ARAs that found them are sent to the autonomous relay system, which NCATS' intramural team has built. There, all of these potential results are sorted and combined as necessary into a set of potential answers for the user. All of these exchanges of information utilize an API standard that was developed specifically for this program, and I'll talk about that in a moment. All these complex systems have to talk to one another, and I wanted to show you this diagram which our teams put together during our most recent in-person meeting. This represents the flow of information within the translator system at runtime. So this doesn't even take into account things like accessing and updating the knowledge graphs that our KPs store. Just all the information that needs to flow between our tools when a query is made to the system. And as you can see, it forms a bit of a hairball graph all by itself. The way in which these graphs get passed around between different software systems is by utilizing the Translator Reasoner API, or TRAPI. It's used to represent the query that a user inputs into the interface, as well as all of the intermediate graphs that are used to construct a result, and then the result itself. It's JSON-based and was purpose-built by our consortium, but has shown utility in other systems as well. Each TRAPI message contains a query graph representing the user's question, a knowledge graph defining and holding data on the nodes and edges that were retrieved from underlying knowledge provider graphs, and a result set with node and edge bindings that reference the knowledge graph itself. These nodes and edges are defined by a complex ontological framework known as BioLink, which Sierra just talked about in depth. This image represents just the node types in BioLink, and it's probably a bit outdated at this point. I'm sure there's more node types in there. But of course, there's a similar hierarchy for the edge types. You can see on the right that we have sort of the most specific entities, things like microRNA to RNA product, all the way over to named thing, which is the most generic concept. This hierarchical model allows translator tools to genericize concepts as needed, so that if a query asked for a specific formulation of a drug, but a different formulation or maybe a dietary supplement might actually fulfill the answer, it's possible for one of the translator software tools to return that sort of related answer within certain limits. The system is robust and covers many data types, but it's not without its challenges. One issue that we've run into, for example, is the fact that the concept of drug is not in the same branching hierarchy as the concept small molecule, even though the vast majority of drugs are small molecules. And so it makes sense from a data modeling standpoint to put those into separate branches, but makes it hard to implement in everyday use. And so we've come up with things like mix-ins and other types of additional relationships between some of these entities that help with that process. I also wanted to show you just a taste of the data sources that we've ingested into Translator. And again, this is not complete. There are more sources than what are shown on this graph. But the Sankey diagram on the left shows a lot of those sources. And to the right is a blown up version of just a section of it. As you can see, we have tons of public data sources, and they're available through different knowledge providers and different overlapping combinations. So for example, the clinical data provider provides information from OMIM and Drug Bank, among many others, while the multiomics provider also includes information from OMIM, but it has mygene.info and the Institute for System Biology's wellness database. So these overlapping sources fit within different knowledge domains, and each of the knowledge providers pull their domain knowledge from those underlying sources. In order to keep all these different data sources straight, knowledge providers and reasoners, all these different data sources, knowledge providers, and reasoners straight, we're utilizing the Smart API registry, which contains registration information for every tool in the Translator ecosystem. It leverages version 3 of the Open API standard and provides annotated metadata about where each tool can be found, what functions they can perform, and what data they have available to be utilized, and then how these data are connected together. Importantly, this is all parsable, allowing one software tool to get the information needed about another in order to utilize the knowledge that it has access to. So if one of our reasoners needs to get data on connections between genes and cell types related to gene expression, it can query the registry for which translator tools have this data and how to format a request for it. Over the course of time since the program's instantiation, we've made incredible strides toward making this system a reality. And now we have an alpha version of the user interface. This user interface interacts with the ARS to display results to users and let them explore the evidence behind and the source of these results. We'll take a look at the interface in just a minute. Now I'm going to give a little history in the project before we look at the actual front end. So I know that a lot of you are familiar with this since this workshop is being organized by people who are in Translator, and many of you are part of the consortium. So feasibility for this program was achieved back in 2019, and at that point we began the current development phase of the program. We began with a competitive prototyping phase in January of 2020, which was part of the final application process, and then once we chose our winners, we began full development of the system in around May of that year. So this means that right now we're just over 3 years into the actual development process. In addition to our development and research teams, we now also have the user interface team, and they're 2 years into a 3-year funding period. We were able to build upon the standards and some of the graphs that were created during the feasibility phase, but for the most part, the development phase represents a new start for the consortium with several new teams and many collaborations that had been self-reorganized during the application process. We also have been holding 2 to 3 hackathon-type meetings each year during the development phase, which for up until June had all been virtual because of COVID concerns. We did have our first in-person hackathon of the development program in June at the Renaissance Computing Institute at UNC Chapel Hill, and we have another in-person hackathon meeting in just over a week back home in Potomac, Maryland. At the beginning of this week, we released our first public alpha version of the translator system. The current version of the system includes functionality for users to ask a specific set of questions of the system and get back potential answers to those questions, along with the evidence and provenance that is associated with each answer. You'll also notice that there's a big blank spot on the right side of this graph. And so at the end of this month, I'm going to be asking the NCATS Advisory Council to approve an extension to the translator program to hopefully fill that timeline in. Now, I mentioned these hackathon-type meetings that we hold each year. We now officially call these relay meetings because NIH doesn't like us to make it sound like we're hacking. And we've held them 2 to 3 times per year every year since the program began. These meetings are true working meetings. We expect that our attendees will make progress toward consortium-wide goals in every session, and so every session has to have deliverables defined so that we can keep track of all that work. Now, as I said, we started doing an in-person meetings again, and though we've definitely perfected virtual meetings as an absolute necessity in this program, an in-person meeting still has its advantages. One of which is that our teams are highly motivated, and you can often find at least a small group working late into the night in the hotel lobby on some idea that they came up with. And so you can see that here. So the image in the top right is Will Bird demonstrating some software he was working on at about midnight that night. And below that is his presentation to the full group about that software the next day. So let's talk about who we're building this system for. We expect our main user base to be translational researchers, particularly rare disease researchers. And it may be that they're in the lab and they observed something interesting in their research and they're looking for potential explanations or support for what they saw before they pursue it further. Or they may be early career researchers with exciting new ideas and they're looking for mechanisms that might support their hypotheses that they can then test more. And we have kind of a built-in group of users as well who've given us a lot of feedback during this initial phase, and that's the analysts working at the PMI, the Precision Medicine Institute at UAB. These analysts work directly with clinical researchers who are looking for new potential treatments for very rare or refractory conditions. And you'll hear a lot more about that from Matt Might, I'm sure, later today. We also have one more very different group of users for Translator, and those are our data scientist collaborators. People who wish to contribute data to Translator and make use of the knowledge graphs that we've built through APIs and other behind-the-scenes ways of interacting with the graphs. So even though our system can, in theory, support almost any query through our Translator Reasoner API, we made the decision at the start of this phase to begin with a set of templated queries in order to make sure that the results are tailored to represent the information that users want to see in their answers. At this time, a user can ask 3 queries. What drugs may treat their disease of interest? What genes may be up or down regulated by a drug of interest? Or what drugs may up or down regulate a gene of interest? Note that the term drug is used pretty loosely here because chemicals that don't have any FDA approval status can be returned in all the results for these queries. Because we utilize a complex system of software tools, all passing graphs back and forth, we also have a relatively complex scoring scheme that had to be implemented, and we are still working on improvements to this right at this moment. Right now, it utilizes a combination of weighted scores coming from each of the reasoning agents that returned a given result. And we're in the process of implementing additional scoring metrics, such as an assessment of the novelty of a given answer, as well as including direct clinical evidence where it's available. So this is what the current user interface looks like. It's important to note that at the top of the page, we always show a banner, making it clear that the system is for research purposes only and is not meant to be used by clinicians as decision support in the course of their typical treatment of patients. That is very important to NIH. This is not for treatment of patients directly. I'm going to walk you through a query so that you can see what this process looks like. I'm going to use the genes to chemicals query shown on the right, which will give us information on relationships dealing with gene regulation between different types of entities. We expect that this query will be often used by researchers like those in NCATS's own division of preclinical innovation in preclinical early stage drug development. And we can also imagine that this will be very useful to research teams who don't have access to large-scale screening capability to help narrow down the chemicals to screen before they start their early drug development stages. We have to specify that we want chemicals that regulate a gene. And then you can see next we have to choose whether it's up or down regulated. So we're going to choose up regulators in this case. And at this point, a search bar pops up letting the user know that it now expects a gene to be entered. I'll use a gene that I'm very familiar with. It's called FRAS1, which is known to cause congenital diaphragmatic hernia. And that's what I studied in my graduate thesis work. When you start typing the name of the gene, the search bar will then update showing the options. And then in order to submit a query, you have to click on one of those options to confirm which gene you're interested in. While you're waiting for results, the system gives you some information about the entity that you searched for, in this case, the FRAS1 gene. And then this is the first page of result that I got back for this query. You can see some basic information on each result, which includes the number of paths that support the result, and we'll look at those in a moment, the evidence that supports it, including publications and other data sources, and the score for the result. I want to also mention that one of the main reasons that we've focused on a small handful of templated queries to start with is because of this results page. For every new type of answer node that we need to show to users, whether it be drugs or genes or phenotypic features or any other, we want to know what, we have to carefully consider what information our user will want to know about that given result. And it also changes the facet filters that show up on the left side. So you need to be able to choose different facet filters for different node types. You can see on this page that the results are chemicals. So we have a filter for different stages of drug approval on the left. For genes, it might instead need to include facets for which chromosome the gene's on, what things like gene ontology categories, things like that. The consideration of how to display results to our users is paramount to our development process at every level. So let's look at one of these results in more detail. In this case, valproic acid, which I happen to know is a pretty decent option for treatment, molecularly speaking, for congenital diaphragmatic hernia. When you click on the little caret on the right side, the result is expanded to show a lot more information on that result. This includes a graph view, which shows all the connections that were found between the potential treatment, valproic acid, and the FRAS1 gene. If you scroll down further, you can also see what we call the path view, which shows all of the pathways that connect the two in more like a table view. This can give you a good sense of what kinds of relationships are represented in the graph above. So for example, valproic acid causes increased expression of FGF10, which in turn causes increased expression of FRAS1. And if you click on one of those green buttons, a screen will pop up showing the evidence for this relationship. So in this case, a set of papers from PubMed. You'll notice that this shows not only the information like the title and journal name, but also a snippet on the right side of text, which is the section from the paper that was flagged as the source for the connection between these two concepts. If you were to click on Read More below any of those, it would take you directly to the publication on PubMed. Now this first view is only for publications, but we have other resources in Translator as well, of course. So you can click on the Sources tab, which will then show you other sources for the relationship between valproic acid and FRAS1, including in this case an entry in the Comparative Toxicogenomics database. If you clicked on the link to the right there, it would take you to a wiki page describing that data source, and from there you can see the link directly to the CTD database itself. One of our major goals, though, for the next few months will be to improve this link-out system to try to send the user directly to the page or entry in the underlying source database, if it exists, that shows the connection. But of course, that's a really huge lift since different databases have very different interfaces to access their information. But we think that we can make it work with a large number of our data sources. And of course, the example I showed you there was a fairly simple one with just a few nodes and edges, but some of our results are much more complex and represent much deeper molecular relationships. This is one result for the query, what chemicals may treat Bethlem myopathy? And as you can see in the result, one of the results, a type of collagenase, is linked through several different genes that may represent a whole cascade of gene regulation that could be examined in more detail by a researcher. And if you were specifically interested in, for example, the collagen 1A1 gene, you can highlight a node and it will show you all the paths through the graph that include that node. Or you can click a node twice to deselect it and gray out paths that include it. Now, I've spoken in the past about exciting outcomes from Translator, including several clinical trials that were initiated from research that started with the Translator query. But some of our more relatable stories come from the work, as I mentioned, of the PMI, the Precision Medicine Institute at UAB Birmingham, who have been part of our Translator consortium since its inception. Dr. Might's going to give you more details, of course, about how their institute works in his keynote later in the day, but in short, their team of translational researchers works closely with clinicians who see patients with very rare or highly refractory conditions, and their analysts use Translator to come up with potential treatments for these patients, write research reports about the results, and give the patient's physicians these suggestions. Key to this is that allows the patient's physicians to evaluate the options and possibly recommend new treatments, often repurposing a drug indicated for some other disease. One such example was a very rare disorder called Shine syndrome, also known as DLG4-related synaptopathy. And as you can see here, Shine syndrome is named for its symptoms, which include sleep disturbance, hypotonia, intellectual disabilities, neurological disorders including motor issues, and epilepsy, and is caused by mutations in the DLG4 gene that cause loss of function or haploinsufficiency. The research team at PMI were asked by physicians working with Shine syndrome patients to look for potential treatments for this very rare syndrome. And because it's so rare, it actually is not found in some of the disease databases that we pulled data from. So they decided to look for potential treatments that may upregulate the DLG4 gene itself in order to compensate for the haploinsufficiency. Translator returned many potential treatments, and the analyst's report suggested a few options that may be worth considering. Based on this report and the doctor's review of it, one of the patients was started on a common blood pressure treatment called guanfacine. After approximately 5 months, the patient showed measurable improvement in both motor and behavioral skills. And you can actually see that in a pretty remarkable way because the patient's mother sent in some images of her coloring books from before treatment and then after treatment. And she remarked to the PMI team that they've seen a huge improvement in Peppa Pig, which I thought is just such a great example of a parent knowing their child so well, but not in clinical terms. We have other examples of results from translator queries that have led to advances at different levels of translational research. We know of several cases where translator results led directly to clinical trials, as I mentioned before, including one for treatment of activity-dependent neuroprotective protein, or ADNP syndrome, as well as trials testing both acute and long COVID treatments. And of course, I would be remiss to not mention the recent surge in research around large language models like ChatGPT and others. We've been evaluating ways in which we might be able to integrate with these tools. While for the moment we're only using a few templated queries in the alpha version of Translator, one of the ways that we hope to expand the query options is by allowing our users to ask a natural language question, have an LLM interpret that question and format it into a query that Translator can understand, and then also summarize the papers that were flagged as being relevant to the result, to give the user a good overall idea of what that underlying evidence might be. There's also the constant question of whether our system is even relevant in the age of LLMs. But I think we can make some very good arguments that Translator will fill a role that LLMs never can for biomedical researchers. For starters, unlike current LLMs, the Translator system will not hallucinate results. Every relationship represented in Translator's knowledge graphs have evidence and provenance information that helps our users understand how relevant that information is to them, and importantly, whether to trust it or to take it with a grain of salt. In addition, knowledge graphs represent a way to traverse and navigate knowledge in a way that LLMs just can't allow. You aren't going to see Google Bard or ChatGPT standing up a graphical interface that lets users explore the underlying data as if it was a map of locations and roads that connect them, whereas we can, and we plan to do so in the future for Translator. So what do we still have in the works for Translator at this point? We will continue to expand the templated queries that we offer for our users, with eventual support for the very generic query, what is the relationship between concept 1 and concept 2? We expect to make significant performance improvements over the next several months, including making the system return results faster and to support many concurrent users as we ramp up our messaging and recruit more users to the system. We also plan to make significant improvements to the documentation available for Translator, including instructions to allow collaborators to include their data in the system and to in turn utilize Translator knowledge graphs through our APIs and other background systems. We're also working on a user guide to help our main users, biomedical researchers, to understand what Translator can help them accomplish given their own work. We're also thinking about ways that we can allow our users to bring their own data into the system and query it using the insights that this data represents, either sharing that data with others through the Translator knowledge graphs or keeping them private. Companies, for example, may have proprietary data that they just can't share widely, but that could lead to important insights that help streamline their drug development processes. So we'd like to allow them to use that data in their searches. Similarly, academic researchers may have data that hasn't been published yet and could lead to important insights. So they could keep that data private until it's published and utilize it in Translator in the meantime. And we'd like to, in general, make it easier for users to pull new public data sources once they're properly vetted into Translator to expand our capabilities. Another exciting concept we're exploring right now is pathway figure OCR, our optical character recognition, which is being looked into by our Translator teams in order to return pathway figures that might be relevant to your query, but also to potentially generate knowledge directly and use the figure as itself as the underlying knowledge source. We would also eventually be interested in potentially generating new figures that represent knowledge connected across different databases, but that's, at the moment, kind of a pipe dream. I want to take a moment to shout out all of my colleagues at NCATS who work on the project. We've built an amazing team with diverse academic backgrounds and expertise, and have combined the talents of both extramural and intramural research sides of NCATS in order to do so. And I also want to thank the NCATS ITRB team, who put a huge amount of effort into helping us deploy all of our software tools to the NCATS cloud stably and reliably. I want to recognize several former members of our team who moved on to other positions, and the entire Translator Consortium, many of whom are in the room right now, for their incredibly hard work on the project. But now that I'm done with my simple explanation of what Translator is, I invite you to go to the URL shown at the top of the slide and try it out for yourself. Note that you'll have to make a user account in order to run your own searches, but you can see results from several example queries, including those focused on several rare diseases, without signing up. And with that, I'd like to thank you for your attention. I'm happy to take questions on Translator.
Questions?
It's a great talk, and I think one of the persistent challenges in Translator is the sheer scope of it, and both sides really, like the amount of data we're ingesting, and also the potential number of audiences we might want to serve. So do you have a sense if who our current audiences are and what our audiences might grow to in the future?
So I'd say right now our current audiences really revolve around the people that we've brought in to sort of alpha test the system. Of course, like I said, your PMI analysts are a huge part of that, but also academics that we've engaged directly with throughout the country, throughout the world, who have specific research concepts in mind that they want to try to understand more about the underlying relationships between. But that said, I think our next set of users are going to have to be real, researchers who don't have any background in computational biology, any background in graphs, anything like that. We want to bring the people who work at the bench to Translator. And I think those early career investigators and postdocs and people like that are really the ones that we expect to utilize a system like ours. You're not going to get the PI, playing around with Translator. They're too busy writing grants. But they're, the postdocs and the graduate students who are invested in trying to find new things to explore in their own research, either currently or moving forward, I think are the people that we're going to really push for.
What if we made it easier for writing grants? So what if we added a mode to make it easier to write grants with Translator?
If we can come up with that, I'm all for it.
It's actually, I think it is kind of like when I write grants, I'm like, okay, I have to figure out everything related to this concept, and I don't want any blind spots. If there is a tool that can help me find my blind spots, it is Translator. So I think there could be a role to attract that audience.
I think that's very, very valuable point, Matt. And I think that I'm not going to go into Litcoin, but I think that's going to be a valuable piece of the pie there as well. Because one of the things that we're doing at NCATS right now with projects like this is making sure that every project that we work on that's in the data science realm is compatible with all the other things we're working on. Because if we don't start building standards for the community as a whole, no one else is going to. So it's really important to me to make sure that the BioLink ontology is utilized in other projects that NCATS and other NIH institutes use, and to see us bring in as many public data sources again that have been vetted as we possibly can, and where we know that there are problems with the data, like we've talked about SemMedDB before, that we come up with solutions to either minimize that data and bring other data in to supplement it, or entirely replace it when possible.
I was wondering,
as like science changes, how do we handle the fact that some of the publications might be out of date? Like with all the COVID stuff, early COVID papers ended up being very wrong. How do we make sure that those results aren't returned and only the right ones are?
So that's one problem that there's no easy solution for that, because as much as we like to think that retractions make a difference, in reality, a retracted paper will come up in searches just as quickly as a paper that hasn't been retracted. And so that's going to involve a lot of work in those underlying data sources to make sure that when a retraction has been issued, that the data is flagged in some way that says, by the way, this relationship is in question at best, right? That's hard for us. That's really, really tough. And I think we have one team called the text mining provider that is working hard on things like that, but it's not an easy thing, and they're in the process of just trying to bring in the types of resources that we need, let alone then trying to actually directly curate them. So I don't know if we have a good answer for that right now.
Because in the work we do with patients, this is a very real problem.
Mm-hmm.
Our practical workaround right now is human analysts that actually have to go read the papers. Maybe this is one place where LLMs could actually provide a big lift by reading the papers, summarizing them, looking for even methodological issues. I don't see any reason why, in principle, this can't be done as at least a first pass to take the load off the humans. Yeah, no, I think that's totally true, and I'm sure you're going to talk about LLMs in your talk later. You're not? I'm shocked. Oh, anyway, so no, I think that we actually do have ways in mind that we can try to address these, but right now our focus with Translator is get it in front of users and find the problems and expand the query space, because with only 3 templated queries, we're extremely limited, obviously, but we did that on purpose, and so now we want to start to expand that query space. Will?
I'm delighted to see that future plans include allowing users to somehow upload their data. I've heard that over and over again from subject matter experts. Another thought I have had for a long time on the system is that in addition to the traditional bench biologists or medical researchers, there's also a bunch of computational people that also I think would benefit from all the curation and models and so forth. So do you also see opening up the system through APIs or having Trappy available to data scientists and computational people, or because the current GUI isn't really intended for them?
Yeah. No, for sure, and creating the documentation to allow data scientists to utilize Translator more is definitely on the list of things within the next year we want to make sure we focus on. At one of the here's the thing with our hackathons, we touch on so many subjects within our hackathons at this point now that it's hard to get a big idea like that drilled down enough to actually get worked on. So that's the type of thing that I expect would actually would work better at what we call a mini hackathon, which is like these one-day virtual meetings that we do, where we pull together people from the consortium and say, hey, we've got this one idea. Can we take it from idea to early code in one day? So we've done those on a few different subjects in the past. We haven't been able to do those in any of those in the last 6 months or so because we've been focused on this public release. But I think that's one place where we have the option for really getting a lot done in a very short period of time. So I think a mini hackathon on opening this up to developers is definitely something we could work on very soon. Yep.
So you had that early slide where you had this axis of biochemical to clinical or something like spectrum. And I reflect on the paper that was put out early in Translator by Christine and Chris Dawson about who is a translational scientist. And I often think, because of people that I'm exposed to, including, I'm married to a public health epidemiologist, a certain individual who will go unnamed who lives locally here in Seattle drove me home after we came back on the airplane on the recent relay. And, like I asked that individual, so when you mean evidence, you mean evidence as in evidence-based medicine, right? Which has all of these PICO attributes, right?
Right.
A certain subset of health people, that's their bread and butter.
Yep.
Where do those people, we talked about them in the Who is a Translational Scientist, but where do they fall into this rubric? I mean, there's other dimensions here that are not represented, right?
Yeah,
We're
no,
going to
that's...
loop those people in and try to we should have some PICO attributes at some point, right?
Yeah, no, that's absolutely true. And I mean, as you know, we've so far we've been able to bring some direct clinical sources, open clinical sources into Translator, but we're not utilizing those data sources enough yet in the way that we really should be. And that's on the horizon for sure, but that doesn't get to things like PICO attributes. That's another level of bringing in that metadata from clinical work. And it's just not something we've been able to attack yet, but I think it's something we should. I don't know a timeline on that one. Though realistically, that's going to be in that next empty space on the funding graph. Realistically, when I fill that space in, hopefully. Go ahead, Chris.
All right. Great talk, Tyler. Following from Will's question, as well as being able to kind of future plans, including the ability to upload your own data and opening up to other bioinformaticians to call via API. Do we have thoughts about opening up in terms of, I want to bring my own algorithms or my own inference procedures, like some kind of plug-in architecture that would make it really easy for people to just, slot in their workflow here?
That's interesting. I mean, we will, in theory, have the capability to do that very soon through the custom query interface that's being worked on right now. Actually allowing it to happen is another question, because we would have to, first of all, develop documentation on how to use that, do in some way vet it if we're allowing it to be accessed by the Translator UI, of course. So I haven't thought about that yet, but again, in theory, it's a relatively small leap from where we are right now. It's more in practice, what safeguards do we need to put in order to make that a reality?
Any more questions?
Following up to Chris, I guess one thing about our architecture and the fact we have a consortium is that we have this, setup where you can have ARAs and you can have KPs and so forth. So I guess that would be another thing that I could imagine over time as maybe the consortium expands, or maybe we have additional reasoning components or whatever that kind of plug in. Do you see that happening over time? Do you see the consortium growing? I'm not talking necessarily about funding or things like that, but maybe other groups that are already doing reasoning or already, providing databases or knowledge
You
bases.
touched on the important caveat there, which is we're not going to be increasing the funding necessarily. I'm going to be asking for similar or slightly lower levels in this next funding cycle, realistically. But unfunded collaborators bring in both knowledge more through knowledge providers and more reasoning through ARAs is absolutely on our list of things to work on.
Okay, great. Thank you.
Go ahead, Steve.
Hey, thanks, Tyler. I'm wondering, are there any comment about other ICs that are showing interest in kicking the tires with, or where you think might be fertile ground for that?
So yes, we've talked to program officers and other ICs about Translator, especially over the last few months, extensively, and there's interest there. Then, of course, also in Litcoin. I think kind of pairing those two projects when I talk about that kind of stuff to NIH, really to other ICs, helps a lot, because they can see both how more information could be brought in and how it can be utilized into the system. So yes. Whether we have any specific other ICs ready to say we're ready to help you support Translator, we're not there yet. I think the Office of Data Science Strategies in the Office of the Director at NIH is absolutely supportive of these kinds of projects and are actively looking for ways that they can help support those kinds of projects. And one of our favorite NCATSians just moved over to ODSS. Literally Friday was her last day at NCATS, and she's going to be extremely helpful in in helping us get projects in front of them that are very valuable. So I expect that to be a collaboration that will expand more over the next couple years.
Great. So Susan Gregorick and her team have continued to keep abreast.
They
of
are
what's
very,
going
yeah,
on.
Susan Gregorick and her team are very aware of both Translator and Litcoin and are very supportive. And like I said, so Christine Cutillo, who was our data science guru at NCATS, has just made the jump over to ODSS, and she's going to be extremely valuable to us over there.
Awesome.
All right. Thank you all so much. I really appreciate it.